In this video, we'll be talking about the final two methods for allocation. We'll be talking about Adams' method and Webster's method. So first is Adams' method. Everything in Adams' method I'll write in blue to separate from Webster's method. We'll be using the same table here for both though. So Adams' method is just the opposite of Jefferson's method. If you understood Jefferson's method, you'll understand Adams' method. So here we have a new table. Again, the total is 26K, but how I've divided it between the different states is a little bit different. So again, the standard divisor is 130 because we take 26K divided by 200 is 130. And we have our standard quotas right here, and they of course add up to 200. Now, instead of lower quota, we're looking at upper quota for all of these. So upper quota of 38.46 is 39. Upper quota of 46.15 is 47. So basically, to find upper quota, what you would do is just take the next highest number, no matter what the number is. So even 23.07, even though this 0.07 is very small, the upper quota would be the next highest number, which is 24. And of course, when you add these up, they're going to be greater than 200. So what you need to do for Adams' method is you'll need to find a new modified quota, and this is going to be done differently. So in Jefferson's method, we found a modified divisor that was smaller than our standard divisor because we wanted these numbers to be bigger. But for Adams' method, we want these numbers to be smaller because what we're going to do is, in the end, we're going to take all these numbers that we found using the modified quota and the modified divisor, and we're going to round them up, or rather than round, we're going to find the upper quota. So we're going to use, for 38.17 goes to 39, 45.8 goes to 46, and we want all of these to add up to 200. So now you're seeing how this is the exact opposite of Jefferson's. In Jefferson's method, we found the standard quota, and then instead of using that, we used a modified quota that made all of these numbers bigger than the standard quota numbers, so that you could now take the lower quota of these, and they would perfectly add up to 200 with no surplus. In this method, we're doing the exact opposite. We're taking the standard quota numbers, and we want to make them all smaller so that we can find the upper quota on each of them, and we can get the upper quotas all to add up to 200. So again, you have to use, the hardest part is using trial and error to find this modified divisor. For me, it just took one try. Luckily, I just used 131, which was just one bigger than 130, and I found these numbers. So now let's go through it. So instead of dividing 5,000 by 130, I divided by 131, which means it's going to be a smaller quota right here, and the same thing for all of these, which means that the total is going to be less than 200 because you're taking a smaller number in each case. So now I'm taking the upper quota of each of these, and it's going to be 39, this is going to be 46, this is going to be 8, this is going to be 84, this is going to be 23. And when I add these all up, just as I expected, or as I made it, it's going to be like this. They're going to add up to 200, and each state gets this many seats. So this is using Adams' method. It has the same flaw in the opposite direction as Jefferson's method. Jefferson's method could cause upper quota violations. This can cause lower quota violations. Let's just see really fast why that's possible. So just for example, let's pretend for state B, I took down here, the upper quota was 47. So let's say when you took the modified quota, this number went down very, very small. Let's say it went down to, let's say, 44.8 instead of 45.8. Now, what would the upper quota be? It would be 45. But using Quota Rule, what does Quota Rule say? Since the standard quota is 46, Quota Rule says that the number of seats that state B should be given should be between 46 and 47, but we gave it 45 seats. So this is a lower quota violation. We're giving it a number of seats that's lower than its lower quota. So basically, Adams' method, Jefferson's method, neither is better. They're just opposites. And one causes lower quota violations, one can cause upper quota violations. So now by far, the best method we're going to go over is Webster's method. So Webster's method is kind of a middle ground between Adams' method and Jefferson's method. So I'm going to do the work for it in purple. So what we do in Webster's method is we just round. So we round normally, how we've learned rounding since we were in elementary school. So instead of doing upper quota, lower quota, all this stuff, we're just going to round, which means that if the residue is 0.5 or over, we're going to round it up. If the residue is less than 0.5, we're going to round it down. Just simple rounding, right? So we do have to find a new divisor for this as well, and you have to find a modified divisor for this as well, so that when you add up all of the rounded numbers, they're going to add up to 200. But in this specific example, so note that it's not in every example, we got lucky and we found that the standard quota works. So let's see why it works. So 38.46, round it. So instead of making this the upper quota row, let's make this the rounded row for the case of Webster's method. So this is going to be rounded. So 38.46 rounded goes to 38. 46.15 rounded goes to 46. 7.69 rounded goes to 8. 84.62 rounded goes to 85. 23.07 rounded goes to 23. 7. So now let's note something. Since the green numbers that were originally here added up to 203, we need to find 3 less than that. And did we successfully find 3 less than that? So we found, oh, this should be a 23. So do we find 3 less than that? So 24 minus 1 is 23, so that's 1 off. We found that 47 minus 1 is 46, that's another 1 off, and 39 minus 1 is 38. So we have subtracted 3, and that means the total of these purple numbers, or you can just check it with a calculator, is 200. So we got pretty lucky here, where you round the standard quotient, the standard quotas, and they exactly add up to 200. But just take a quick note that this will not happen every time. Sometimes it'll add up to 201 or 199 or something like that, in which case you'll have to find a new divisor. So just experiment with different divisors that are close by. Usually 131 or 129 will work. Experiment with different divisors, and then you have these modified quotas, and then using these numbers, you'll do the rounding. So you'll have a new rounded list, and these rounded numbers should add up to 200 if the original ones did not. So this is good, because if you get lucky like we just did, and you find that the rounded numbers come straight from the standard quota, that means each state is apportioned, or it's given, it's allocated a number of seats that's within 0.5 of their standard quota, right? Because this 38.46 is within 0.5 of 38, because that's how rounding works conventionally. This 7.69 is within 0.5 of 8, and 0.5 is a pretty small margin of error if you think about it. It's for most states, even states that have small populations like 1K, 0.5 isn't going to be like that huge of a percent of their population. At least not as big as we had with the paradoxes, all those violations and stuff like that. So the last note on Webster's method is that it is also possible to cause quota rule violations, both upper quota and lower quota violations. It's possible, but it is rare, very rare. It happens much less frequently as the Adams method and the Jefferson method can cause lower quota and upper quota violations. So Webster's method is a very good middle ground. So again, with Webster's, Adams, or Jefferson's, the trickiest part is finding a good divisor that's going to do the trick for you. So once you find that, if you have a computer, it should be able to do it within a few seconds. But even if you don't have a computer, it shouldn't take you that long. These methods are very good. So any of them are pretty good. Just stay away from Hamilton's method, because that can cause many paradoxes and is very messy. So hopefully this mini-series on allocation is a little bit helpful in seeing how to give indivisible objects, such as seats, to different states.